Okay, it's sharp 2, so we start.
Yes, ma'am.
A very good afternoon, respected Datar sir, our eminent speaker for today's technical workshop on Hyphenated Technique GCMS, my dear colleagues of FIIC Department Bioanalytical Sciences, teachers from Khalsa, from other colleges, researchers, as well as the industry professionals. I welcome you all on behalf of Guru Nanak Khalsa College for this workshop. Let me just give you a brief idea about our institute. Guru Nanak Khalsa College was founded in the year 1937. So I'm proud to say that we have completed 82 academic years and we have been serving the society and creating leaders. If we talk about the last decade or last few years in research that we have done, we are recipient of several awards. We have got the College with Potential for Excellence Award by the UGC. We are recipient of the Star College status by the DBT, wherein we inculcate the research culture in our students right from the UG level. We are CIRO recognized, and by DST they have been awarded the FIST grant. By NAC, we have been graded as A with a CGPA score of 3.54. And in totality, at Khalsa College, all of the teachers and all the fraternity works on the basic principle of essence of wisdom is service to humanity. I'm happy to share that at Khalsa College, we have some of the most unique and industry-oriented courses. To name some, we have MSc in Bioinformatics, MSc in Nutraceuticals, 2 years MSc in Bioanalytical Sciences, and my own course, 5 years integrated course in Bioanalytical Sciences, which the students can pursue after 12th itself. It gives me pleasure to share that FIIC has completed or is actually completed a decade of success, of growth, of learning, and we are exploring even the more. Our students are in various pharmaceuticals and research setups and are doing good. And in this attempt to celebrate a decade of existence and growth, we are conducting the lecture series. So when we were thinking of the topics, MS was the most crucial one, because if we talk about MS, mass spectrometry, it has become the go-to technique. And it gives us the answers to a range of analytical questions, you know, with respect to offering the sensitivity, the selectivity, as well as the specificity for a range of biological samples, therapeutics, or we call it environmental samples, etc. It is the most crucial technique, so to say, especially when it comes in the discovery and the development of biological drugs. And keeping this entire background in mind, we thought that all the researchers, all the industrial professionals need to harness the knowledge of this particular technique to grow and to bring about or contribute to the scientific community. And that's why we chose the topic of MS to GCMS, and on 28th we'll be having LCMS. So with this little background of the event, I would now go to very much privilege to me of introducing the speaker for today's technical webinar, Dr. Ajit Ganesh Datar. Datar sir pursued his MSc in 1971, after which he received the Department of Atomic Energy Fellowship the same year, and he pursued his doctoral research at BARC. He started with ACC as the research officer and dedicated 12 years of service there, post which he worked with Chrome Line and IR Technology as the technical director and senior manager for 15 long years. He was also associated with Thermoelectron as the general manager for advanced mass spectrometry, where he was responsible for promoting the advanced MS products of the thermophenogen in India. He gracefully retired in the year 2007 and joined the Shimadzu Analytica India Private Limited, where now he's serving as the advisor. His main profile is to provide the instrumental analysis support to the customers and provide training. Datar sir has been the pioneer who has developed several methods for characterization of catalysts and the process products using catalysts. He indigenously developed the BET surface analyzer as well as the particle size analyzer. He's an amazing teacher and he has been associated with and also across of India, including the big IITs. He has several publications to his credit and has successfully guided 8 research students so far with Khalsa College. With this brief background about Sir, I think we all are eager and energized to start with the lecture. I'll just hold on for a minute. Am I audible to all? Am I audible to all, please?
Yes, ma'am.
Yes, ma'am, you are audible.
Okay. So I think the introduction was audible. So I can now request Datar sir to start with the talk. Everyone can hear me, right? Datar sir is not there.
Yeah,
Yeah,
ma'am,
Datar
he
sir has
connected.
joined.
Just now he connected. Yes, sir.
Yeah, okay. Yes, welcome, sir. Yes, sir. Sir, you will have to unmute yourself. Sir, unmute yourself. We cannot hear you, sir.
Yeah.
Yes, sir. We can hear you now, sir.
Hello, no problem. Yeah. Okay.
Yes, sir.
So I will go ahead now. Okay.
Yes, sir. Please.
Thank you, Dr.
Over to
Kavita,
you.
for your words. Yeah. Okay. Thank you. Thank you so much. Sorry
Yes, sir.
for some inconvenience in between. And I hope everybody else is there, especially those who have decided to join for today's this particular talk. All of you are there on the other side and able to get me properly. Assuming that I am proceeding, and first thing is let me thank Khalsa College and all this team of Dr. Kavita for allowing me to talk to all the students and all the people who are interested in such kind of a talk during these days when nothing else is possible to be done, and trying to share some knowledge with every one of you by doing these kind of webinars. So let me begin. I know this is a time odd. It's 2 o'clock after lunch, and this is the time to go to a little nap after the lunch. but all of you are here. Okay, but one possibility, as it is presentation when I cannot see you, because when I teach in the college, in front of me also sometimes students sleep. Here, I'm not able to see you all at all. So it is good that you can also probably sleep. And I also can sleep because you also can't see me. But of course, there is some difference between your sleep and my sleep. Yours could be SLP and mine could be SIP. I can have sleep of tongue or sleep of mind. And probably if you don't sleep, you will be able to catch my sleep. Okay, so let us see who catches who sleep, and let us start my presentation. Somebody has his, um, please mute that because some background is coming. Okay, so this see that you mute your system. Okay, so the voice won't disturb everybody else. Okay, so I proceed now, and I know I have to cover this topic in 2 hours. Hyphenated techniques are many. I have listed few of them here. So GCMS I have listed first, and then there are many more techniques. LCMS, which I am going to do day after tomorrow, and then there is ICP-MS, LCFTIR, MSMS, LCNMR. I'm going to definitely cover GCMS-MS and LCMS-MS in today's and tomorrow's talk. So these MSMS part will come in, and then other techniques probably it is not possible to cover in these 2 days. Okay, but then there are many more techniques, even more than what I have listed. Okay, so so many hyphenated techniques are there. What is the use of hyphenated techniques? We'll see that. Okay, this is what I always show. He is nothing but analytical chemist like me, who is playing with some 5 objects and trying to balance himself on a platform which has a gyratory motion. He's playing with some important terminologies in analytical chemistry: sensitivity, selectivity, separation, structure, and speed. These 5S, I consider they are the most important S of analytical chemistry. As most of you probably know the meaning of it, but still I will just quickly cover some of them because there are students, probably industry and other people will know it, but students may have to understand some of the concepts which I have listed here. Sensitivity is the lowest amount which can be analyzed by a given instrument, and sensitivity can be very low. It could be in femtograms to sometimes to even attograms at one time. So it's every now and then it is going down, and one can detect at very, very low level, and instruments are becoming more and more sensitive with time. Selectivity is something which is also equally important, because if you can determine your analyte of interest in presence of so many other things, your method or your instrument is supposed to be selective. And many times you require that kind of a selectivity when your matrix is tough. You require some kind of a separation. Even if you have a very selective method, you require to do some kind of a separation of your analyte from the rest of the matrix. And separation could be simple techniques like precipitation, filtration, centrifugation, and things like that. And then it could be techniques like liquid-liquid extraction, solid-phase extraction, solid-phase micro-extractions, etc. And of course, the best technique for separation is chromatography. Structure is very important in many cases. You need to know what is present and how much is present sometime. And especially in the areas of drug discovery, finding out the active ingredient from the medicinal plant, to find out which drug the sportsman has taken before the event, and whether he has worked under the influence of any kind of a drug. So you require to find out that. You require to find out which poison has been taken by somebody who has suicided. So you require to find out that compound and structure of that. And all this information, whatever you want to achieve, you have to do it as fast as possible. Especially in industry, it has to be very, very fast. In industry, if you ask them when you want to have a result, mostly you will get an answer, I want the results yesterday. So that kind of a speed is required in industry. So all these 5S are very critical. And if you want to play with this 5S, something needs to be suppressed. Some of the errors need to be suppressed. And what needs to be suppressed? First thing is sampling error. When I talk about sampling error, I talk about 2 things. One thing is whether you have drawn your sample correctly, whether it represents the bulk or not. That is one part. And second part is how you have prepared your sample. If you have done extraction, is your extraction complete? If you have done anything else, then you have to make sure that all that procedure which you are going to do for preparing your final sample before you introduce onto the instrument, you have taken proper precautions to come up to that stage. So sampling error can happen anywhere there, and if that happens, then your instrument may be good, you are very good as a chemist, but still you will have some problems in getting good results. Then there would be a background that needs to be suppressed. So background is always going to be there when the matrix is difficult. So when you analyze something in a matrix like blood or plasma, or when you talk about pesticide residue in food, the matrix is definitely going to be very difficult, and that can give you some background interferences, and that can affect your analytical results. So background needs to be suppressed. So that definitely many a times is taken care when you prepare your sample. But then if it is not done, or even if it is done, some background will be always there, and you have to overcome that background. You have to find out a way so that the background is less at a particular position, and you try to get your work done under those conditions. Analytical instruments always give you some kind of a noise. Whether you want it or not, there will be a noise associated with any signal which is given by the analyte. So the signal and noise both are together, and that is why when we define sensitivity, we always talk about signal to noise ratio. So the noise becomes important, because if you reduce the noise, your signal to noise ratio will be good and your sensitivity will be good. So noise has to be reduced. So this, when it gets completed, you then get good results from your analytical tool. So unless and until you suppress these three things, you will not be able to balance with those 5 years properly. So this is just basics of analytical chemistry, which I have learned, which I have been teaching for last 25 years. When I started teaching analytical chemistry to diploma in industrial analytical chemistry, which was conducted in Ruia College, I was teaching there since 94. So I introduced this concept at that time. And this is the picture which I have drawn. This cartoon is drawn on a transparency. That is why you are seeing that background there. And that then was taken onto the PowerPoint after that. Okay. So yes, so this is what I want to talk to you about in the beginning. And most important thing is, all these 5 years are possible only when you have a hyphenated techniques like GCMS or LCMS, because many other techniques which do quantitative analysis do not give you structure, but this is the technique which also gives you structure. It definitely improves the sensitivity in terms of whatever measurements you do in comparison to the original chromatography technique. So it gives you better sensitivity than GC or LC. It gives you definitely better selectivity than GC or LC. It does, of course, the separation power of GC or LC is used, but within the mass spectrometer, you can have a separation. So it adds to the separating power of your GC or LC. Of course, as I said, it gives you structure, and the speed of analysis can be improved because of the combination of GC and MS, or LC and MS, or MS kind of a technique. So this is, when you have this kind of hyphenation, GC with MS or LC with MS, it is not 1 + 1 = 2. You are getting 1 + 1 = 5 or 10. So it's much better information you can achieve when you have a combination of GCMS or LCMS. Okay, so that is what I thought of talking to the students about these techniques. Yes, so this is a history of GC, LC, and MS. Okay, both together, all the three things together. So LC and MS both started together almost in the beginning of 2000, so 1903, and here also it is 1905, 1906. J.J. Thomson first used mass spectrometer, and Mikhail Svet, whom we know and who is the father of word chromatography, he started the work during that time. And LC and MS both started together. Somewhere in between, in 1941, Martin and Sinch published one paper on the liquid chromatography, because before 1941, from Mikhail Svet's work till 1941, people were working on the liquid solid chromatography. Nobody tried to have liquid coated inert solid and use it as liquid-liquid chromatography. Martin and Sinch started with that. And in that article, they suggested that so far we are using liquid as a mobile phase, but the gas also could be mobile phase. So in 1952, same Martin with James introduced a first gas chromatograph, and that is how the gas chromatography started. And within 6 years of development of a GCMS came into existence. So GCMS was much faster. MS was at that time probably 59, so somewhere around 55 years old, while GC was only about 7 years old, and the GC and MS combination came into existence within few years of development of a GC. And then GCMS grew very fast initially because it was giving lots of advantages, but that itself it made it possible to have LCMS, because there were only 10% compounds which could be vaporized and analyzed by GCMS, while most of the compounds which were non-volatile, they were to be analyzed by HPLC. So for majority of the compounds, the mass spectrometer was not possible to be connected to LC, and that is why people were trying to have LCMS, and it took time, but then finally they developed. More about that part, we will have a look at it when we meet day after tomorrow. Fine, so this is about development of GCMS. What happened? I'm going back, sorry. Okay, so why we want to connect chromatography to mass spectrometry? Chromatography gives you only one dimension, that is retention time. So if we get a particular compound eluting at a particular retention time T1, and then when we introduce our sample, and if you have a compound which also elutes at the same time T1, then you can say that this compound may be present. You cannot say it is present, because there is a possibility that there could be many compounds which can elute exactly at the same time. So you have to have a little cautious kind of a sentence saying that this compound may be present. Well, when you connect to mass spectrometer, this chromatography to mass spectrometry, you get additional information which is called as molecular weight. So the mass spectrometer definitely gives you molecular weight. Now you have two dimensions, that retention time is matching and the molecular weight also is matching with that of a standard and that of your compound. Then you can say that yes, probably this compound could be present. I'm again using some word of cautious, okay? But when we have fragmentation of that particular molecular ion or molecule, and we get what we call as a mass spectra, which gives the fragmentation information also, that molecule is fragmented to give these kind of fragments. And when this mass spectra matches with that of a standard, with that of your compound, then you have more confidence in saying that this compound is present. So that is what the mass spectrometer gives you, these kind of dimensions which are not possible by chromatography alone. And that's the great advantage of having a combination of GCMS or LCMS, or for that matter, any hyphenated technique. Well, this is about a GC, those who are familiar with GC, and I hope most of you are familiar with GC, and that is why you have come to attend a talk on GCMS. I can talk for length on GC itself, but then my major interest is to talk on mass spectrometry. So GC has carrier gas, then flow controller, then you have injection system where you introduce sample into a heated injection port. Sample gets vaporized if it is in a liquid form. It goes to the column oven, which is kept at high temperature so that no condensation happens. It comes out to the detector. Detector senses whatever is coming out, gives a signal, and you get a chromatogram. This is just a cartoonist view. I like to draw cartoons, so I've used whatever skills I have there to make some cartoons like that. Well, so these are the applications, and applications are given in just a brief list. These are nothing but applications of even GC, and that is getting extended to mass spectrometer. Only what advantage is that mass spectrometer can do these applications at much higher sensitivities. Okay, so that's the great advantage. This is a detector of GC and its comparison with MS. Okay, so you can see most of the detectors are here. You can see FID. Yeah, so you can see FID, which has got a very high linear dynamic range. and it can go down to something like the nanogram level. While if you have ECD, you can go down to even less than picogram level. NPD can go down to that level. FPD can go closer to that level. But when you have MS, MS can go even below ECD, and it has much better sensitivity compared to any other detector. One more advantage is that as far as GCMS is concerned, MS is a universal detector. In case of GCMS, MS can determine the organic compounds, it can determine the inorganic compounds, as well as it has no special specificity like your ECD has for halogenated compound, NPD has for nitrogen phosphorus containing compound, FPD has for sulfur and phosphorus compound. So such kind of specificity it doesn't have. And that's the great advantage of MS, that it gives you higher sensitivity for all types of compounds. You can see GCFTIR, that is another hyphenated technique, but you can see its sensitivity is even poorer than FID. So when you have such a kind of a hyphenation available, it definitely gives you some advantage, because FTIR also can give you structural information, but it did not pick up basically because it is not found to be good quantitative analysis tool. And in today's days, we have sample which is available at very, very small quantity, and then we have to determine something in what is available at microgram level. Then FTIR with GC finds a difficulty, and that is why it is not as popular as the GCMS. There are hardly any institutes and industries who use GCFTIR. Well, we require to have an interface between the two techniques, GC and MS. So earlier days, people were using a pack column. So while using a pack column, the flow rates in pack columns were something like 20 ml to about 60 or 80 ml per minute carrier gas flow. So with that kind of a flow, if this flow enters into vacuum system, because mass spectrometer works under vacuum, so when it enters into vacuum system, what would happen is the system will not work properly because so much of gas is entering into it. So that is why combining a GCMS with GC having a pack column, you require some device which is called as jet separator, which was used at one time because there were pack columns available. So when GCMS was first evolved during 1956 or 57, and the first commercial system came out in 1959, people were using this separator, which is called a jet separator. Now, jet separator has two jets in front of each other with a very fine gap between the two. And then the GC flow comes from one end. As it comes out from this small jet, the lighter carrier gas will move in all directions because it will diffuse very fast, while heavier molecules of your sample will travel straight, and then they will enter into the area this which is connected to mass analyzer or mass spectrometer, and then the carrier gas is removed to the maximum extent, and the sample gets concentrated, comes into mass analyzer, and that is how you can get rid of the carrier gas which enters into the vacuum system of mass analyzer, and that makes it possible to work with a pack column. But today we don't work with pack columns. We always use the capillary column. Even for general applications, we use capillary column. So when capillary column is used, the flow rates are about 1 ml per minute or 2 ml per minute. And these small flow rates can be easily taken care by the vacuum system of a mass analyzer. So you don't require a jet separator like that. What we require is some kind of heated interface which is between the two systems, because GC is one box, MS is another box, and between these two boxes there is a small portion which is heated, and through that heated portion, the capillary of the column of a GC enters inside the ionization chamber of a mass analyzer, and that is how this interface, a small interface, is used, and which is just heated, and that's all is the kind of a device which is required when you connect a GC to mass spectrometer. So let us look at the brief diagram and the components of a mass spectrometer. So we have a sample inlet. Sample inlet for us is GC today. Then this is what we call as interface between GC and the mass analyzer. From here to here, this is a mass analyzer with its vacuum system. So these molecules enter into ionization chamber or ionization method, where the molecules are ionized, and the ions of this molecule, they get into the mass analyzer, because mass analyzer can only understand two things. It understands ions in a vapor phase. So these two things are important for mass analyzer. It wants whatever comes inside should be in a vapor form. It cannot be in liquid form. It cannot be in any other form. And then if it has to measure that whatever is coming, it should be charged, because any charged particle or any charged, what we call as ions, can be separated by applying electric or magnetic field, and those ions will get separated on the basis of the mass to charge ratio. So the mass of the molecule, mass of its fragments, all will come here. Mass analyzer will separate the molecule, the ion of that molecule, and the fragments which are also ions on the basis of their masses to charge ratio. All those ions will enter into detector. Detector will count each and individual ion on the basis of its mass to charge ratio. What you get is a mass spectra, which will be plotted and analyzed by a data system. You require a very high vacuum in this area, because this vacuum ensures that whatever comes into mass analyzer, whatever gets ionized and comes into mass analyzer, it should not have any kind of a collision with any other gases. If there is a air in this area, what will happen? The vapor ions of the molecule which is produced here, those will interact or collide with the air molecules if they are present around in this area, and then they will not be possible to be separated in mass analyzer. So to avoid all that, the entire system right from here to here is kept under very high vacuum. Okay, so that the ions can move from the ionization chamber through the mass analyzer to the detector and get detected. So this vacuum system is very much essential for mass spectrometer. Well, we come to the ionization and how the ions are produced. Okay, so we have types of ionization. One is for volatile samples, other is for non-volatile samples. For volatile samples, we have two methods. One is called as electron ionization, other is called as chemical ionization, and that is used with GC. So we know that GC is the one which is used for volatile samples, and for non-volatiles or for thermally labile compounds, we generally use LC. So non-volatiles and the ionization for non-volatiles, which can be analyzed by LC and then connected to MS. This part we will cover in day after tomorrow's talk. But what we are going to cover is this part, where the components which are eluting from GC come to the ionization chamber. EI or CI will ionize those, and then they will enter into mass analyzer. So ionization is the most important thing in mass spectrometer. Okay, so I used 3 punchlines to explain 3 techniques: GC, LC, and MS. If you ask GC what you can do, GC will tell you that if can evaporate, I can separate. If you ask LC what you can do, LC will tell you that if you can dissolve, I can resolve. And if you ask mass analyzer what it can do, mass analyzer will tell you that if you can ionize, I can recognize. So if you know these 3 punchlines, you know almost all the techniques very well. Well, if the compound is non-volatile, and if you want to analyze it by GC or GCMS, you need to convert it by derivatization to a volatile compound. So there are methods for derivatization. Some of the non-volatile, some of the highly polar compounds or highly thermally labile compounds can be converted by derivatization to volatile compounds, and then they can be analyzed by GCMS. So that is one technique which is possible. It can be also used for normal GC analysis, and it can be definitely used when we want to do some GCMS analysis also. Well, we have, as I said, we'll get into the ionization techniques for GCMS. EI, electron ionization or electron impact ionization. Now, most of the time people just call it as electron ionization. Very rarely it is called as electron impact ionization. The word impact has lost its impact, so it is not used much. And we just call it as electron ionization and chemical ionization. Let us try to look at each technique now. So electron impact ionization or electron ionization is the one where we use a very high energy electrons, which have energy of 70 electron volts, which are bombarded onto the molecule. And the energy 70 electron volts is very close to about 1600 kilocalories. 100 kilocalories are sufficient to break any sigma bond. So you are providing a very high energy. It is called as very hard ionization. You are bombarding it with very high energy electrons. So what you can expect that all sigma bonds, which only require 100 kilocalories, will break down. And what you get is only carbon, hydrogen, nitrogen, oxygen, sulfur, etc. So only elements will get formed, and you will not get group of fragments, but you will get the, the fragments like atoms itself. So, but that doesn't happen. What happens is, because of these high energy electrons, the internal energy of the molecule increases, and then it starts breaking. And because of that, the fragmentation happens, but it doesn't fragment to a great extent. And what we get is the fragments which can help us in finding out the structure of the molecule. So electron ionization is mostly widely used technique for GCMS, suitable for volatile compounds, as I said, suitable for coupling with GC and probe, not really coupled to LC today, earlier because there was only EI which was possible at one time. So people tried to use it with LCMS also. So particle beam, thermospray, moving bed, many of these earlier old LCMS techniques used EI as ionization source even for LCMS. Electron ionization, as I said, it is highly energetic process, produces M plus radical. What does it mean? From the molecular ion, the electron is knocked off because of the bombardment of electrons. So the electron which is hitting the molecule, the outermost orbital of the molecule, it will remove the electron from there. The heating electron also will go. The electron from the molecule also will go, and you will get a M plus radical. Radical because the last orbit now has only one electron, because one electron is lost. And because of that loss of electron, the molecule as such will get a positive charge. It will become a positive ion. So that's what happens. In addition to that, this M plus ion breaks to give you some abundant fragment ions. So it breaks to give you the fragmented ions. Okay, so those ions also then can be used for separation. And then there is one more possibility. I am contradicting my own statement, M plus radical, and M plus not always visible. So sometimes if the molecule is very fragile, what may happen is this ion will not be seen. You will only see fragments. This will not get formed at all. It forms and then breaks, and there will not be any kind of concentration of this in the fragmented ion. So you will not see it at all. Okay, doesn't matter, but whatever information you get, it is still possible to be put into library, and then there is a library searchable spectra. Why it is so? Whenever you use this default 70 electron volts energy of electrons bombarding onto any molecule, you every time get exactly the same spectra. On the same machine after a few days, on any other machine manufactured by anybody else, anywhere in the world, you will get, when 70 electron volt energy is used, you will get same spectra for the same molecule. That means that information is sort of a universal information that can be stored in the library, and you can build up the library for all known organic compounds. And there are two commercial libraries. One is called as NIST, other is called as Willy. And these libraries have more than 3 lakhs of organic compounds and their spectra stored. And that will help a chemist who is trying to work on GCMS to analyze his sample and then search the compound from the library and look at the structure available from the library and try to match both of them and come to a conclusion about the structure of the compound which he's trying to analyze. So that's the advantage of electron ionization, that there is a library searchable spectra possible. So this is how it works. You have a filament to which a current is passed. Because the current is passed through this, it gets heated and it will start throwing electrons. Now these electrons will go towards the anode, and then they will get deposited, discharge here. But on the way, they will come across the molecules which are coming through your column, of course, along with carrier gas molecules, and then hitting these electrons with those molecules, they get ionized, and then these ions are pushed into mass analyzer, which is on this side. So these ions, molecular ion plus fragment ions, everything will enter into the mass analyzer, which is on this side. So that is how the ionization happens in electron ionization. Let us take some example. We take an arbitrary molecule ABC, and when it is bombarded with electron, it may get excited. We are not interested. Then it gives you ABC plus 2 electron, the one original electron plus the electron which has come out from ABC molecule. Then it can get fragmented to give AB plus, BC plus, AC plus, A plus, B plus, C plus. So when you get such kind of fragments, each of these fragment gives you the molecular weight of this. When you get ABC plus, you get a molecular weight of this compound by itself, because loss of electron will not change its molecular weight. BC plus will give you the molecular weight information about half of that, or 1/3 of that, or 2/3 of that. A plus, B plus, C plus. When you get this kind of information with the molecular weights of each of them known, what you need to do is you have to assemble them and come to a conclusion of structure of this ABC molecule. Let us look at one example which I have put here. This is a compound which is called acetophenone. So this is phenyl group. I consider it as A. This is CO group, which I considered as B, and CH3 group I considered as C. So this is that same molecule which we talked about, ABC. Now when this ABC gives you ion, molecular ion, by losing one electron, the molecular weight of this compound is 120. So you get a peak at 120 mass. That is what we call as molecular ion, M plus radical. Then I'm getting a peak at 105, which is, when I look at this spectra, this is called as a molecular ion because it is the peak which has got maximum mass on the x-axis. So there is no mass beyond this. So this could be my molecular ion. Then I'm getting this peak 105, which is a stable ion, and it has got highest intensity, and the loss between these two, the difference between these two is 15. So we can say that this ion is formed by loss of this 15. So it is nothing but AB plus. So ABC plus has lost C, so it has given AB plus C. Now this is 77. This is nothing but A. So it has given A plus BC. Then there is another one which is 43, which is B and C. If you combine, the molecular weight is 43. CO plus CH3 is 43. So you are getting 43, which is BC plus, and A is neutral. So you get, here you can yourself see in this simple mass spectra, there is ABC plus, there is AB plus, there is A plus, there is BC plus, and knowing all these masses, you can find out what could be this compound. And this is a simple compound. It is definitely there in the library. And when you look at the spectra in the library, it exactly matches with this. You know that you are working with a compound called as acetophenone. And that is how the spectra can be read very easily. This loss is 15, this loss is 28. It could be because of CO. This itself is 77. So there is C6H5, the phenyl group. So all such kind of information, and 43 is because of COCH3. So this is how you can look at the spectra and try to analyze and try to find out the structure of your compound if it is not available in the library. Well, we go to next ionization technique, chemical ionization. Why it is necessary? Because we have said in one of the statement earlier that it sometimes does not give me molecular ion. If the compound is fragile, molecule is fragile, it will not give you molecular ion. It will only give the fragments. And you are interested in the molecular ion also, because the molecular ion helps you to find out the structure better. Now, when you are working with unknown compounds, are maybe not found in the library, you definitely need to have a molecular ion. It is like solving a jigsaw puzzle. If I give the kid some 20 pieces and ask him to assemble a picture of that, it will find it very difficult because I have not shown him the final picture. I only have given him some 20-30 pieces and told him that this will make a picture. You make the picture. It is very difficult. But if I give him a picture, I show him the picture, this is how it looks. I printed that picture and put it in front of him. And now he knows how to assemble those pieces. Now it will help him to find out the way to come to that picture. Why it is possible? Because the picture is known to him. So similarly, if molecular weight is known to you and you know only the fragments, then you know how to assemble these fragments to come to this molecular weight. And that is how the molecular weight information is very essential. and that is why we require some soft ionization technique which will not fragment that molecule totally, and you will get a molecular ion. So chemical ionization is such a method, it will give you definitely a molecular ion. We use some kind of a reagent gas there, like ammonia or methane or isobutane, which is admitted into the same ionization chamber. Electrons are bombarded onto this reagent gas, they will get ionized, and then these ions will interact with the molecule of interest, and the molecule gets ionized. In the process, molecule gets a proton added to it, so it becomes a positively charged ion, but with increase in molecular weight by 1 unit because proton is added to it. So the chemical ionization works in this way, that you require some kind of a reagent gas. So it is definitely similar to EI, development from EI, gives a molecular weight definitely, can give structural information, it can give some fragments sometimes and can give you structural information, and it produces M plus H ion. What you require to have? Choose reagent gas according to compound type, not reproducible from lab to lab, hence there is no CI libraries. So in case of chemical ionization, there is no library because the fragmentation will change depending upon the gas which you have chosen. The fragmentation will change depending upon pressure of the gas which is admitted into the ionization chamber. It will also depend on the temperature during the ionization. So whatever temperature you have kept your ionization chamber at. So there are a lot of factors which are responsible for the fragmentation which may happen in chemical ionization to some extent, and then that cannot be every time reproduced. So there is no CI library. It works like this. Now you have same kind of a setup which we have already seen. We have the methane gas admitted. You have the sample coming from your, this gets ionized. Now sample comes from your GC column. It gets ionized, and then these ions are pushed into the mass analyzer, which is again beyond it. There is some lensing system. These are the lenses which are made up of metal rings with a positive charge on the metal ring. So what will happen? When ions are pushed through that onto this side, they have to pass through this metal ring which has a positive charge. These are positive charged ions. So positive will be repulsion. So they will try to go through the exact center of this ring. So they will not get diverted here and there. So you get focused beam of ions into the mass analyzer because of this lensing system. It is working like spectroscopy, because in spectroscopy you have the you have a polychromatic beam of radiation which comes and falls onto the grating. Grating will separate them, disperse them into individual wavelengths, and then you can take a spectra and you get a spectra of absorption at individual wavelengths. Here we are doing a polyionic beams which will enter using the lenses onto the mass analyzer. Mass analyzer will separate these polyionic beams into individual ions, and you will get individual ions recognized, and you get information which we call as a mass spectra. So that is why the system is called as mass spectrometry. Fine. So let us see how the whole thing happens in case of a methane gas. So methane gas initially, as I said, is bombarded with electrons. With 70 electron volts, it produces CH4 plus 2E. CH4 gives CH3 plus H. The next reaction, which is called a secondary ion, CH4 plus interacts with another methane to produce CH5 plus and CH3. It can also produce C2H5 plus. Remember this. Okay, it also gives C2H5 plus. And then the last reaction is that the CH5 plus here interacts with the molecule of interest to give you MH plus. So this is how the protonation happens, and the molecular weight of molecule increases by 1 unit. So this is what we call as positive ion chemical ionization, where the proton is added to the molecule to give you a positive molecular ion with proton added to it, increasing the molecular weight by 1 unit. So CH4 also, yeah. So I've written here the reaction of CH5 plus can ionize neutral analyte molecule M by proton transfer, hydride abstraction or charge exchange. So RH plus M give R plus MH plus. So that is how proton transfer happens. Sometimes you may get M minus H plus, so that also can happen. So you will get hydride abstraction here, and because of hydride abstraction, minus H goes, you get this has a plus charge. So this kind of a reaction is very rare. What you get only is the MH plus. So positive ion can also obtain by using the isobutane. So this is a reaction for isobutane, because we can use 3 type of reagent gases: methane, isobutane, or ammonia. Now in case of isobutane, you get C4H10 plus, C4H10 plus another C4H10 give you C4H9 plus. Okay, so this C4H9 interacts with the molecule to give you MH plus. So again, it gives you proton added, but what you get is C4H8. This is the isobutene which gets formed as a neutral. So this is how you get here also. With isobutane also, you get MH plus. Similar reaction we can write for ammonia. So NH3 plus gives you NH3 plus electron gives you NH3 plus 2 electron. NH3 plus reacts with another NH3 to give you NH4 plus. And this NH4 interacts with molecule of interest to give MH plus and NH3. So this is what happens when we have the ammonia as a reagent gas. But every time what you get is a protonated ion. These are all different gases or chemicals which are hydrogen, isobutane, methanol, propanol, and everywhere there is some proton affinity, and that is very important. Okay, so this is important. This number is important. Now, why this number is important? So these are the methane. It is proton affinity of methane is 552, 821 for isobutane, 858 for ammonia. Okay, so let us see what is the statement. Proton affinity of a molecule should be more than proton affinity of a gas, reagent gas. Then molecule M will carry the proton. So this is how the reaction is important. If the proton affinity of the molecule which we are analyzing, if it is more than proton affinity of the reagent gas, and reagent gas affinity is given here. So if reagent gas affinities are this, your analyte molecule should have proton affinity more than this, so that it will form a MH plus. Okay. Then there is a negative ion chemical ionization which is also possible because of the bombardment of electron onto the reagent gas. The energy of these electrons reduce to 0.4 electron volt, 0.5 electron volt, etc. So when you have low energy electrons, now these low energy electrons can interact with molecule if it has got electron affinity to produce M minus charge. So here electron gets added onto that, and there is no increase in molecular weight. The molecular weight will remain intact. It will remain like that with a negative charge, and mass analyzer is capable of analyzing positive as well as negative ion. So we can measure the positive ions as well as negative ions by using a mass spectrometer. So we talk about positive ion chemical ionization where proton is added. So we get definitely molecular weight information. It gives you increased selectivity for many compounds. Selectivity affected by reagent gas. So depending upon the quality of the reagent, depending upon the nature of reagent gas, you can get better selectivity. So for ammonia, you can get better selectivity for nitrogen containing compounds. Isobutane gives better sensitivity for hydrocarbons. So there is some kind of thumb rule about selecting the particular reagent gas. Methane is mostly preferred for 2 reasons. Methane is a gas at room temperature, while 2 others need to be heated because the isobutane is a liquefied petroleum kind of gas. It has a lot of impurities also, so people don't prefer it. And ammonia is also reactive gas, so again people don't prefer it. So most of the time people use methane as a reagent gas. Let us look at this mass spectra of these 2 compounds. These are tricyclic compounds, amitriptyline and cyclobenzapine. And you can see both these compounds by EI with 70 electron volts as energy do not give you molecular ion. So there is no 277 here, there is no 275 here, hardly anything here. So we are not sure what is the molecular weight of this particular compound if it is unknown. But I want to find out what is the molecular weight. I can go to positive ion chemical ionization where proton will be added and you will get a molecular weight information. So when I do positive ion chemical ionization, PICI, I get a molecular weight information. So 270 has become 278 because of proton addition. 275 has become 276 again because of proton addition. And the peak intensity is so high that I can easily tell that these are molecular ion. So this is 275 and this is 277. So positive ion chemical ionization definitely give you information about the molecular weight of a compound if it is not possible to be measured by electron ionization technique. There is a negative ion chemical ionization which has also a great advantage. It gives you molecular weight information. As I said, direct molecular weight information, no proton addition. So it is very simple. Can be 100 times more sensitive than positive ion chemical ionization because it is working like electron capture detector. Electron gets captured by the halogenated compounds, and electrons here are produced because of the electron bombardment directly. While in case of GC, we use electron capture detector with radioactive element. Here, it is not necessary to have radioactive element. Electrons are produced by bombarding electrons onto the molecule through the filament, and you get much higher sensitivity for halogenated compounds. It is very selective towards halogenated compounds, as I said, ideal for analytes in a complex mixture. So if you have a complex mixture containing halogenated compounds and non-halogenated compounds, and then if you work with normal GC or normal GCMS with EI, you will not be able to differentiate halogenated compounds from non-halogenated compounds. But if you use now negative ion chemical ionization, halogenated compounds will show much higher sensitivity. So the peaks will be easily seen now for halogenated compounds compared to non-halogenated compounds. So it will give you the simplification of the analysis of complex mixture by using negative ion chemical ionization technique. So we have ionization summary. We can have M plus electron gives you M plus. So the electron is lost and you get M plus. M plus RH give you MH plus. So proton addition is one way of ionization. M plus electron giving M minus is one way of ionization, and M plus A, that is called as adduct ion, giving Ma plus. So sometimes, as I have told you that in case of methane, there is a C2H5 plus getting formed. So this C2H5 can interact with neutral metal A plus, and you can get Ma plus. So many times when we have a higher pressure of a methane in the ionization chamber of a GCMS system, you many times come with MC2H5 plus also in addition to MH plus. So you'll get MH plus as well as MC2H5 plus when you use methane as a chemical reagent or chemical ionization with little higher pressure of methane added. You will get Ma plus, that is called as adduct ion. And many times these adduct ions are very important, and when we get into LCMS, adduct ion is very common there. So we already know components of mass spectrometer. We have already covered ionization. Now we enter into the mass analyzer. So measuring masses, we have a unit which is called as one mass unit called as AMU, atomic mass unit. It is also measured in terms of Daltons. It was previously when, because of the J.J. Thomson who invented mass spectrometers, some people started calling us TH as a unit for atomic mass unit or Daltons. And some people called as 1000 part of AMU, so millimass unit. And then sometimes it is also referred as M by Z. So most common things which we use are AMU, Dalton, or M by Z. Mass spectroscopy, it gives you atomic and molecular weights are generally, okay, so atomic and molecular weights are generally expressed in terms of atomic mass unit. The atomic mass unit is based upon a relative scale in which reference is the carbon isotope of 12, which is assigned to have a mass exactly 12 AMU. In fact, you can say it is 12.00000 AMU. So it is assumed to be 12. And with respect to that, the masses of all other elements is calculated. And one AMU then is 1/12 of a mass of one neutral carbon atom. Mass spectrometry is perhaps one of the most widely applicable of all the analytical tools available to the analytical chemist, in the sense that this technique is capable of providing information about so many things. Okay, so it can just, because this is the first lecture, I thought of putting this slide here. The qualitative and quantitative composition of both organic and inorganic analytes in complex mixture. This instrument measures compounds with molecular masses up to 200,000 daltons or even beyond that. The structure of wide variety of complex molecular species. It can give you isotopic ratios of atoms in sample like carbon 12, carbon 13, or nitrogen 15, nitrogen 14. So these kind of isotope ratios can be found out. The structure and composition of solid surfaces can be found out. And then the accuracy and precision of the measurement is excellent. It can give you isotopes. Some isotopes is nothing but same number of electrons and protons, different number of neutrons. They have different masses, so they will get separated in the mass spectrometer. So mass spectrometer is able to separate isotopes. What are the components of MS? What is mass spectra and identification and quantification by MS? So mass spectrometer is an analytical instrument that answers the question, what is in the sample, how much is present, for a very wide range of samples. So it can do qualitative analysis, it can do very good quantitative analysis too. I'm not going through this because this I already covered, this is covered. So I'll directly go to what is a mass spectrum. A mass spectrum is the relative abundance of ions of different M by Z produced in an ion source. It is a chemical fingerprint. It contains molecular weight information generally, as we have seen. Most of the time it gives molecular weight information. Sometimes it doesn't give because the molecule is fragile. It gives you structural information mostly because it gives you abundant fragments which will help you to find out the structure of compound, and it definitely gives us the quantitative information. There are so many mass analyzers: magnetic sector, quadrupole, ion trap, Fourier transform, time of flight. There are a lot of hybrid mass analyzers like quadrupole TOF, trap TOF, and so many. Okay, so orbit trap has come, and so there's so many mass analyzers which are there, and it is very difficult to cover all these mass analyzers in one lecture, and that too when we talk about GCMS. So I'm only going to cover two mass analyzers here, maybe three. I will cover quadrupole, ion trap, and maybe time of flight. So I have covered to some extent magnetic because it was the first kind of mass analyzer, and that is why probably I have put it. So in magnetic sector mass analyzer, you have ion source. This is the horseshoe magnet where the magnetic field is acting vertically like this. So what happens when the ions come into magnetic field will start acting on the ions, and the one which is smaller will be pulled by this magnetic field downward. So that is why this has M by Z lower. As you go here, this has got M by Z higher. So the mass of this is higher, mass of this is lower. That is how all the masses what we have, they get separated. So this is highest mass, this is lowest mass. In between, other masses are there. Now, if we want to measure all the masses, we can have detectors at all these places. But generally, which is not done, we put the detector at central place here, and all others are moved to this trajectory by changing the magnetic field or by changing the acceleration voltage. That is the voltage by which we throw the ions here. What we are doing, we are throwing the ions here, and once they are thrown, because of the pull of this magnetic field, they start coming down, and depending upon what throw we have done here, what energy we have put here to throw that, depending upon that, the ion will get, one ion will come to the center and go. If I change the acceleration voltage, then probably I can make this ion come here and go to the detector. So one by one, I can make every ion to come to this trajectory and go to the detector. So I can change the acceleration voltage here, keeping the magnetic field constant, or I can keep the acceleration voltage same, but by changing the magnetic field. So if I have this ion which has a low mass, and it is coming at this, and if I want to make it reach here, I will lower the magnetic field so that this will have less effect and it will go up and get detected here. So by scanning the magnetic field, I can make all the ions measured one by one at one single detector at this end. Okay. So this is the ion source. Now here it is not only magnetic field which is used, it is called as double focusing magnetic sector. So we have used magnet, we have used electric field, and ion source is here. We throw the ions inside, they travel like that, they travel this free zone and come to the electric field. From the electric field, they go to the slit here. From there, they go to the detector, and detector will sense them. So this is how the double focusing magnetic sector instrument works. And there is a formula for that. I'm not going into all that because of the time, but you have to remember the last formula, which is this m by z is equal to this into b square r square upon v, where b square is the magnetic field, v is the acceleration voltage, how we have thrown the ions inside, r is the curvature or the trajectory radius. And if we know this, you can calculate which m by z will give me this r, or at this radius of curvature, which m by z comes out. Knowing value of v and b, we can calculate that. So by this way, we can measure the m by z value by scanning the magnetic field or by scanning the acceleration voltage. Here there are two examples I had given for some of my students when I used to teach, that what magnetic field strength would be required to focus a beam of carbon dioxide ion, CO2 ion, mass 44, on a collector of a mass spectrometer whose analyzer tube has a radius of 31.45 centimeter, assuming voltage of 1000 volt. So what is given is this, what is given is R, and what is asked is magnetic field. We know m by z because CO2 is 44, so z is 1, positive, only one positive ion. So we know this, we know this, we know this, so we have to calculate the magnetic field. Next is similar example, same example above, change your magnetic field strength by minus 10%. So whatever magnetic field we get here, we change it by minus 10%, so lower it. Then what voltage puts CO2 ion into the collector? So radius, keeping radius same, what voltage needs to be applied so that the same CO2 will follow the same trajectory and go to the detector of a mass analyzer. So these kind of examples can be analyzed and sorted out or solved in the exam. Quadrupole mass analyzer is the next mass analyzer, which is the most popular mass analyzer. Magnetic sector machine is outdated as far as GCMS is concerned. It has very limited application as far as GCMS is concerned, and that is for dioxin analysis by using a high resolution mass analyzer. Now, what is the difference or what are the problems with respect to this mass analyzer, which is called as a magnetic sector mass analyzer? There is one great advantage of this system is that it gives you very high resolution. That means whatever molecular weight you will get by using this, it will be up to 4th decimal level. So you will get molecular weight something like 120.4786. So you will get molecular weights like that by using a magnetic sector machine. So it gives you accurate mass, it gives you high resolution, it helps you to find out structure better because it is giving you that kind of a molecular weight information. And then whenever you register a new molecule, you synthesize a new molecule, you have to register it, you require an accurate mass to be put into the literature. For the registration of that compound in the dictionary of chemical compounds, you require the accurate mass measured by high resolution mass analyzer. Okay. So there it is useful. It has very high cost. It requires a huge room for its installation. You require a big chiller because magnets get heated. You require a chiller for cooling the magnets. So all these kind of things which are required. You require a lot of lensing system. You require very high vacuum system because the total amount of volume which to be degassed is very high. So because of that, this mass analyzer is not so popular. Cost has, and the skill which is required for operation and the cost, all of that made it outdated to some extent. And what is used now is a quadrupole mass analyzer. So this quadrupole mass analyzer has 4 rods, as you can see, and these rods are very compact. They are about 20 to 25 centimeter in length, about 8 millimeter in diameter. These are 4 rods. And what we do is we apply DC and RF voltage onto these rods. Ions come from one end into the field. This is called as quadrupole rod, and the field generator is called as quadrupole field. What we do is we apply a DC and RF voltage. DC is direct current, RF is radio frequency voltage. So in such a way that if these 2 rods, opposite rods, are positive at one moment, these 2 rods will be negative at that time. Now, if these two rods which are negative at one time, they become positive, at that time these two will become negative. So the charge is rotating like that. And then what happens is, if the ions enter into this quadrupole, at a particular DCRF voltage, one particular ion will get stabilized in the field and go to the detector. At that DCRF voltage, all other ions, as shown here by the ion in red color, will go out or will get discharged onto the rod. Maybe at some other DCRF voltage, this ion will get stabilized and go to the detector. At that time, the ion shown by green color may go out. And that is how, one by one, I can measure all the ions by scanning this DCRF voltage, so that I measure all the masses of the compound which I have put into mass analyzer, which got fragmented in ion source. All those fragments come into my quadrupole, and I can get a mass spectra as I scan this DCRF voltage. And the spectra which I shown you for the acetophenone is measured by using a quadrupole mass analyzer, scanning it from low mass to high mass. This kind of a instrument, quadrupole mass analyzer, can go up to something like 1000 Daltons or 1100 Daltons, that is 1100 molecular weight. For GCMS, that is sufficient. For LCMS, the quadrupole mass analyzer can go up to 2000 Dalton. But for GCMS, most of the molecules, they are possible to be analyzed, are only up to maximum 800. All other molecules above 800, they have either very high boiling points or they decompose before their boiling point. So they are not possible anyway to be analyzed by quadrupole. So we require, for those molecules, we require LCMS. But then quadrupoles are generally going up to 1100 Daltons, and they can measure all the ions which are possible to be measured from, say, 10 mass unit, atomic mass unit, to up to about 1100 atomic mass unit by scanning this DCRF voltage. Now, one thing we have to remember, as I can scan this DCRF voltage to make sure that all the ions which have got formed in the ionization chamber to reach the detector one by one, I get a good mass spectra. Then there is one more possibility, that if I can keep this DCRF voltage constant for, say, this ion which is green, so I'm not scanning it, I'm fixing it in such a way that only this green ion will go to the detector continuously. So I can measure only green ion. I don't measure any other ion. I don't get a mass spectra. I can only measure this green ion, a single ion. And when I operate this mass analyzer in this mode, it is called a single ion monitoring. So I am interested in monitoring only one ion. Why it is so? Because I know what I'm measuring. I know that this compound has this ion, and I want to do a quantitative analysis of this. And in this mode, which is called a single ion monitoring mode, I get maximum intensity of this ion, because I'm not losing that ion at all. So I will be able to measure that continuously without any kind of a problem. So this is how the quadrupole can be used in two modes: scan mode and SIM mode. And scan mode is used for qualitative analysis. SIM mode is used for quantitative analysis in general. Okay, so quadrupole mass analyzer has all these advantages, that it can operate in scan mode, it can operate in SIM mode also. Now, how this works? So as we said, we are applying DC voltage, we are applying RF voltage, and DC voltage and RF voltage is applied. If we only apply RF voltage, all the ions will pass through the quadrupole and go to the detector. There will not be any separation. But when we apply DC voltage, the ions will start moving in all the directions. And then at a particular DC RF voltage, one ion gets stabilized. It comes on this is called a stability line. And then this ion can be detected at this DC RF voltage. This ion will get detected at this voltage. When it comes here, this is the ion which will get detected at this. But then when you look at this stability line is not a good line, because when you look at 219, there is a very big range in terms of the mass also. So it gives you a low resolution, it gives you high sensitivity. But when I do it, when my stability line I change in such a way, now if I have a stability line going like this, I will be able to measure 219 more specifically, 69 more specifically, 28 more specifically. And in this way, I can have a better resolution but then the sensitivity may drop because number of ions reaching the detector will drop. Okay? So quadrupole can be used in this way, and by applying a DC voltage and RF voltage, you get the signals like that. It can be explained in another way also. When you apply a positive DC and negative DC, so what happens? There is something called as when you apply a very high positive DC voltage, what happens is all the high mass ions crash. I do not know how to explain you on, I think I can go back and explain you on this quadrupole. So if I am changing a DC voltage, what happens, suppose a large molecule has come here, large ion has come here, it has to go straight, but then I'm applying a DC voltage. What will happen when I apply DC voltage, and when DC voltage is positive and this ion is positive, it will try to go to negative. Suppose at that time this is negative, so it will try to go to this negative. Suddenly when this becomes positive, it will go here. But being a heavy ion, it will not be able to divert so much. When this again becomes negative, it will start coming here. When it again becomes positive, it will start going here. And finally, when this becomes negative, it will drop here. But by applying a proper voltage, I can make it go like this and go to the detector. So at one particular DC voltage, some particular ions will be lost and some particular ions will be able to go to the detector. So there are two ways. I mean, this gap which is shown here, so high mass crash and low mass crash. So when the DC voltage is on minus side, the low mass ions will crash. And there is some in between region. When these voltages are proper, this slit, what you can call as, this can move from this region to this region slowly. So all the masses can be detected. So here you cannot measure these masses. Here you cannot measure all these masses. What you can measure at this particular condition, only masses which are in this region, m by z value, they can be measured. And this can be slowly shifted. So you can shift it from low side to the high side. So when it is here, on this side there will be low mass crash, and on this side there will be high mass crash, and only some small molecules will be able to go to the detector. And that is how all the masses can be measured. Okay, so this is the Nobel Prize which Paul received for the development of a ion trap. Okay, and he is the fellow, Wolfgang Paul, his name is. He received a Nobel Prize for developing ion trap, but he did not receive a prize for developing quadrupole. So he is the one who developed both quadrupole and ion trap, and he received a Nobel Prize in 1989 for developing ion trap. So this is ion trap. In ion trap, you have a ring electrode and two end caps, and the ions come from one end and get into the trap, and they move into the trap. This trap has a RF field, so ions will be in this trap and they will circulate in this trap. When the field becomes positive, they will come to the center. When the field becomes, this ring electrode becomes negative, they will start going here. So they will be rotating in this. So they will be in this circle. They will be trapped here in this circle for some time. And when you start applying the DC voltage onto these ring electrodes, they will see the pull from this axis. So if this is XY plane, they will receive a pull from the Z axis, and then they will be out, because to this end cap there is a hole from where the ions will come out and go to the detector. So the ions enter from here, come into the trap, they are stabilized in the trap, then they are removed one by one by applying a DC field onto this ring electrode, and then they are measured. So in this way, you can measure the ions, and as the ions are trapped here, they don't get lost because they will be here, and one by one they will get out. So you will have a very high sensitivity in a scan mode, but it will not be able to give you good sensitivity in SIM mode, because in this, SIM is not possible at all. Another advantage of ion trap is that it can do MS. So when we go to MS, I will talk about how to do MS in ion trap. This is what it does. You can do multiple stages of MS followed by MS raised to 4, like that. It can do MS. What is the advantage of MS and why it should be done? We will see at the end of this presentation. GCMS also. Now this is a time of flight mass analyzer, where called as TOF, 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 and the letters with which it is starting, time of flight. Okay. Now in this time of flight, there is a plate, metal plate, which we can apply a very high positive voltage. Ions come from one end in front of the plate, and we apply a pulse of positive voltage to the plate. Now what will happen? The ions will start moving, because all these are positive ions. We apply a positive voltage to the plate, they will start moving in this direction. Now what will happen? All the ions have same kinetic energy equal to 1/2 mv square. Now masses being different, if this has a low mass, it will have higher velocity to keep that 1/2 mv square constant. So this low mass will have higher velocity, it will move fast and go to the detector. The heavier mass will have less velocity and it will go slowly. And that is how the separation happens in this time of flight. There is nothing else except this plate to which we apply a positive field, and on one side there is a detector. There is no other control in between. The ions move freely in this flight tube, which is under very high vacuum, and that is because of the push applied from one end. And what we measure is the time taken by the ion to move from here to the detector, and that time is in microsecond. And once this analyzer is calibrated, it gives you the mass of whatever is coming first, whatever is coming second, whatever is coming third. Remember one thing, for every mass analyzer, a mass calibration is required. Like in spectroscopy, we do wavelength calibration. Unless and until we do that, we cannot say that this particular compound has a lambda max of this. Similarly, unless we do a mass calibration, we will not know which mass or whether my molecule has this particular mass or not. So mass calibration is required in every mass analyzer, and that has to be understood. We quickly go to the detection of the ions. I will only consider two detectors here. One is photomultiplier and other is electron multiplier, and also maybe a microchannel plate. So almost everything I'm considering. Okay, fine. So electron multiplier, it's a conversion diode which is able to convert either negative or positive ions into electrons. These electrons are amplified by a cascade effect in a horn-shaped device to produce a current, and this device, also called as channeltron, is widely used in all the machines. Okay, so this is a discrete kind of a electron multiplier. So these are all diodes, and one by one, as number of diodes are more, every diode, the electrons get multiplied. So positive ion hits the conversion diode, gets converted into electron, and then these electrons get multiplied on every diode here, and then you get a signal. So this is one way of electron multiplication. Other way is this. So this is a horn-shaped device. So as the ions produce the electron travel within the horn-shaped device, and every stage when it strikes this material, it will get multiplied, and at the end of the tunnel, you have the anode to which it gets deposited and produces a current which is amplified. And for every ion which hits the diode, you produce one electron, and for every one electron there is 10 raised to 6 or 10 raised to 7 number of electrons formed, and that is how you get a signal, very strong signal. This is multi-channel plate ion detector. So whatever these holes you are seeing, these are enlarged here. So this is nothing but the same electron multiplier. You can say at every stage it is getting multiplied and finally comes out as a signal. So these are all channel. This is why it is called as channeltron, because there is micro channel plate. So each one is a detector by itself. So in case of time of flight, you can put it because it's a tunnel through which the ions are moving, and all the ions will come together if they have same mass and hit here, and they can get detected by this technique. Microchannel plate, array of tiny channel electron multipliers, usually glass capillaries coated with electron emissive material. No scanning necessary, mass of ion is determined, so that is what it does. Disadvantage, it has poor resolution, expensive, and short lifetime. So this is what the channeltron looks like. Okay, so this is time of flight to which this channeltron is put. Okay, this is the old design and this is the new design. So new design has no area here between two channels. There is hardly any area here. You can say between two channels there is some area which is not useful area. Okay, so we do not want that. We want maximum area to be used for detection. Diode photomultiplier tube is another detector which is used, where you have a normal photomultiplier tube which you use in spectrophotometer. And in spectrophotometer, your photon is converted into electrons, and electron gets multiplied in the dynode inside. And that is how the photomultiplier tube works. Here also, it is the same kind of concept is used. So initially, whatever ion is coming from mass analyzer is converted into electrons. Electrons will fall on the phosphor, which is able to produce photons. And then these photons get into the photomultiplier tube and give you a signal. So this is how it works. Ions will convert into electrons. Electron will fall on phosphor. Phosphor will produce photons. And then these photons get into photomultiplier tube and detected. So what you do is you first convert ion into electrons, electron into photons, photon into electrons again, because photomultiplier tube understands electrons. And then you have 2 times conversion of electrons. So in all that process, there is a good chance of losing sensitivity. And that is why it is not used to that extent. Electron multiplier is used more. So every mass analyzer requires a system, and you should know what this vacuum is and what kind of components and pumps which are used in creating this kind of high vacuum, which is of the order of 10⁻⁵ to -6 torr. Torr is nothing but 1 millimeter. So you produce such a kind of a high vacuum in case of a mass analyzer. Now you remember the initial pressure in a GC is more than 1 atmosphere, or at least say 1 atmosphere. So that is somewhere close to about 1000 millimeter. And you are going down to 10⁻⁶ millimeter. So 10⁻³ to 10⁻⁻⁶. So you can see there is a difference of 10⁸ times you are going down in vacuum. So your vacuum system has to be very good. So one device which is always used is a rotary pump. And this rotary pump is put below the table where the machine is kept. And the machine works in such a way that this is a rotor. It is a spring-loaded rotor. This is a spring. And what it does is that as the rotor moves, it takes the air from the system, takes it down, takes it further, and it is given from exhaust out. Okay, as the air comes like that, as the rotor moves, every time air will come here and get out. As this moves further, it will come here, take the air from here, from the system, take it out. So every stage of a movement of a rotor, this spring-loaded plunger will move and it will take air every time. So that is how it works, and it gives you a vacuum level of -3. Once you get a -3 vacuum, your turbo pump starts. Okay, I'm not going into diffusion pump because of the time. I'll directly go to the turbo pump. And in turbo pump, you have the fins here, and these fins are made up of very thin aluminum. They rotate very fast. It has a very high RPM. And what happens? Whatever air is on this side will by and will go out. So this is connected to the system directly. From the system, it takes air, and then it takes it to rotary pump, and rotary pump will take it out into the atmosphere. So this sits inside the instrument just below your mass analyzer. You require some gauges to measure the vacuum, because there is one condition which is there in achieving the vacuum, that unless you achieve the vacuum level of -3, your turbo pump will never start. So to get the vacuum of -3, you have to wait for some time. And once the turbo pump starts, the vacuum is very fast, because the turbo pump speed is very, very fast. But then how to measure that you have reached the -3 vacuum? So for that, this Pirani gauge is used. It is nothing but it works on a thermal conductivity principle. So if there is a gas inside the chamber, it will have a higher conductivity. If there is a very less gas, or if the vacuum is close to -3, the amount of gas available for conduction will be less. So the less current will be produced, and then the calibration is done of the gauge on the basis of that. And then you can see the vacuum. And if it comes below -2 and goes to -3, your turbo pump will take over. Then turbo pump will start, it will start giving you vacuum, and it requires another gauge because the Pirani gauge gives you vacuum only -3. Paining gauge works on the principle of ionization. So it has a cathode ray tube which is connected to the system also. And as the vacuum level goes -3, and once this pump gets on, the ions are produced in the cathode ray tube by bombarding electrons onto the gas molecules. They will produce ions, and the ion current will be produced. If number of ions are less, that means you have a very good vacuum of -5. Number of ions produced will be less, ionization current will be less, you get a high vacuum, and that is how it can give you vacuum which is up to the -9. So -3 to -9 torr, the penning gauge can give you vacuum. Well, we have come up to all the components of a mass analyzer. Now we have to talk a little bit about, I'm not going into the fragmentation and structural elucidation in detail because that itself will require many lectures to cover that. So I'm only going to cover some basic aspects of fragmentation and structural elucidation. Okay, so let us see what it is. So if you have a sample to be analyzed, how do you proceed? There are 3 types. Run the spectra you get against a database, that is library. Don't stop here. Obtain a high resolution spectrum if possible. We are talking here for the molecule which is new, which probably may not be there in the library, but still you are working with the condition that you have a library, you look into the library. Don't stop here. Try to get high resolution mass spectra, which will give you molecular weight up to 4 decimal. So your chances of getting the molecule will increase. And apart from that, follow this, or if you do not have this, follow this interpretation here called as SIP, and make sure that your identification is self-consistent. So you should follow the fragmentation regulations, rules, and look at all the fragments. Justify why this fragment should come for this molecule, and on the justification done by that way, you can come to the conclusion that this is my structure of the molecule which I have. So this is the way generally MS interpretation is done. There are some basic rules. So isotopic intensity of carbon-13. Now remember one thing, that there is always a carbon-13 associated with every carbon, and this carbon-13 is a stable isotope. It is not radioactive. Carbon-14 is radioactive, and it is in real stresses. You can't measure it under normal condition. Okay, but carbon-13 is always there because it is 1.1%. For every 1 carbon, there will be 1.1% of carbon-13. Now that helps a lot, because if I have 10 carbons in my compound, then carbon-13 peak will be 10 into 1.1, because 10 into 1.1 will be carbon-13. So 10 into 1.1 means 11. So if my carbon-13 peak is having 11 units extra at the molecular ion peak very next to that, that means this compound has 11 divided by 1.1 will have 10 carbons. So I get some information about my compound, that this compound has 10 carbons in that. Okay, I'll show you this. Here is the example. Now this is the compound where relative intensity of carbon-12 is 50.01. Relative intensity of carbon-13 peak is 4.52. But what is the mass? This is X mass, this is X plus 1 because of carbon-13. Now what I do is, this is 50.01. So I have to convert it into 100. So I have multiplied everything by 2 so that I get everything to that level, roughly by 2. So if you multiply 4.52 by 2, it will come to 9.04. So that's the X plus 1 intensity is 9.04. So 1.1 into number of carbon gives me 9.04. So 9.04 divided by 1.1 will be 8. Now number cannot be odd, so there is, this compound has 8 carbons in that. That is how I can conclude on the basis of just carbon-13 peak. Just measure the carbon-13 peak height and convert it to 100% if the original peak is not at 100% level, because with respect to this 100, this should be calculated. So with respect to this as 100, this will be 9.4. And if this is 9.4, 9.4 divided by 1.1, because carbon-13 abundance is 1.1. So I am converting that, and number of carbons here then will be 8. Okay, so that is how it can be calculated. So if I give you some simple thing, that if the 100% intensity with respect to 100%, carbon 13 peak is 16.5%. How many number of carbons are there in my compound? So it is easy, 16.5 divided by 1.1, and it is so simple division that it will come to 15. That means if carbon 13 peak is 16.5 height compared to my main peak, then I have 15 carbons in that compound. So that is how this carbon 13 isotopes helps you in finding out the structure of a compound to some extent. So M+1 peak also can come not only because of carbon, it can come because of hydrogen, because hydrogen has a deuterium, which also is 1+1 isotope. It can come because of nitrogen, because nitrogen 14 and nitrogen 15. But the abundances of these peaks are very less. This is only 0.016. This is 0.36. But number of nitrogens in given compound will be very less, while number of carbons will be very high. So this is more significant. Others are not that significant. But then they contribute to M+1, and that is why in that example we got M+1 peak 8.2, because there was some contribution coming from hydrogen as well as nitrogen. Okay, so we have to take into consideration that aspect also. M+2 peaks also can come. So the carbon 13 itself can give you 2 peaks, because there are two possibilities. There could be 13 carbons in a given compound, and that has also some possibility. And there is oxygen 18, which also contributes to M+2 peak. And you can calculate M+2 peak intensity by this formula. There are so many other isotopes of importance. You can see carbon 13 fell, but is actually consider it as 1.1. Nitrogen is here, 0.369, that was taken. And then you see 24 is 4.5%, so quite significant. But more significant are chlorine and bromine. Chlorine is almost 30%. So this is 3, this is 1. 3:1 ratio. Chlorine 35 and chlorine 37. This is M+2 peak. 35, and difference between 35 and 37 is 2. So if this is M, this is M+2. Bromine also 79 and 81. If this is 100, this is almost 100, 97. So this is 1:1 ratio. This is 3:1 ratio. So bromine has 1:1 ratio, where M and M+2 peaks. Here M and M+2 peak, the ratio is 3:1. So that is advantage if you get 2 peaks in your spectra for molecular ion, and the ratio of the first peak to the next peak, which is at M+2 unit, 2 mass units ahead, if the 3:1, that means there is 1 chlorine in your compound. If the ratio of M and M+2 peaks is 1:1, that means you have 1 bromine in your compound. That is how you can do the calculations, and you can get some information. This is 1:1, this is 3:1, and this is for sulfur, and there is nothing else than that. Okay, fine. So I'm giving you some examples. Now this is one example which is for bromine, and this is the compound where there are 3 bromines, like bromomethane, tribromine, bromoform, and there are 3 bromines. And when you have 3 bromines, you get 4 peaks because of 3 bromines. You can see here 237 because all the bromines are 79. You get 279, 181. This 279, the middle one 81, and like that there are 3 combinations here. There are 3 combinations here, and there are all 81 one combination. So they are 1:3:3:1. So that is how they are there. So you can see here there is 1:3:3:1, which is because of CHBr3. Then 1 bromine is lost, so there is a loss of 79. And now you have 2 bromines. They come in 1:2:1. Here there is 1:1, so 1 bromine is lost. So like that, you can calculate the presence of bromine in a given compound. Okay, so this is CHBr3. This is again one example. No, I'm not. Yeah, this is not so. This is some funny example where it is compound which is called as decabromobiphenyl. Now this is a very big compound. There are deca means 10 bromines onto 2 phenyl groups attached to each other, and you can see the molecular weight if you calculate on the basis of 79. it will be 934, and you don't see 934 at all. But what you are seeing is all M plus 2 peaks. And the most common would be, because bromine is in the ratio of 1:1, when there are 5 bromines of 79 and 5 bromines of 81, you get this 944. And this is the major peak. And this is because of 5 bromines, 29, 5 bromines of 81 in this compound, you get 44 as a mass. Now, when I run this as a standard, I got this, and when I run unknown, I get this kind of a mass spectra. I'm sure that this is nothing but decabromobiphenols compounds. These compounds, the decabromobiphenols, are used in as a flame retardant, and they are highly toxic, carcinogenic, so they need to be determined. Okay. There is something called as a nitrogen rule, and that probably is known to many of you, that if a compound has molecular weight which is odd, then the compound should have minimum 1 or 3 nitrogen, 3 or 5 odd number of nitrogens. If the molecular weight is even, then there could be 0, 2, 4. That means even number of nitrogens. So for even number of nitrogens, you may not be able to decide. But for odd number of molecular weight, you can definitely say that the compound definitely has 1 or 3 or odd number of nitrogens. So nitrogen rule tells us about the presence of nitrogen in a given compound. If the molecular weight is odd, there is a good chance, or there is a chance, of course, there is a surety that the compound will have 1 nitrogen in that. Okay, so that is how, at least minimum 1 nitrogen in that. So that is why examples are given. If you calculate the molecular weight of this or molecular weight of this will be odd, this will be even because it has 2 nitrogens. So it will be even. So here we cannot say it has nitrogen definitely. But when the molecular weight is odd, we are sure that the compound has a nitrogen in it. So I'm not going into rings and double bond. It is going to take time. So most elements have distinct isotopic intensities. MS is the best technique to find out those isotopic intensities. We can recognize the pattern given by carbon, sulfur, chlorine, bromine, etc. Apply simple formula to calculate the isotopic intensities, and you can calculate relative abundances, and that will help you to find out the structure of the molecule only on the basis of isotopes. Now, if you go into the fragmentation rules, there are lots of them. And if we want to look at McLafferty rule, and we want to look at the other rules like retro Delader and so many of them, it will take very long time to get into that. So I will stop here and I will go to what the GCMS can be used. One is it can be ion chromatogram. It will look like a chromatogram, because FID also is ion chromatogram. Whatever gets ionized in the flame, you get a chromatogram. Here, whatever ions are produced, they get detected by the detector. You get a total ion chromatogram. It will look like a chromatogram. So you will get the intensity against time, and you will get usual peaks. Okay, so that is one thing which you get from your GCMS. Second thing you can get is the full scan. That means when you click on any particular peak in your chromatogram, you get a scan or a spectrum. It is part of the scan of any compound which you are able to get on total ion chromatogram. And then if you want to do a single ion monitoring for quantitation, you should know what is your molecule. You should know which ion you are targeting. And if you put that ion and ask it to monitor, it will only give you a chromatogram for that ion, and it will omit all other ions. So this becomes very selective for the compound of your interest. It will only find out the or the ion which has this ion. If it doesn't have it will be at that retention, because the detector doesn't see that. So that way we can use single ion monitoring selectively to look at one particular ion. Using standards, we can calculate the area of that peak and the area of the unknown peak, and then look at the quantitation of that particular compound. So these are very important scan events. So this is a chromatogram, which is a total ion chromatogram. This is what we can do with the SIM. We have taken a particular beam, and total ion calorigram shows a very small peak, but when you look at seam, you get a very strong peak because it only sees now this particular ion. Okay, so that's the advantage. This is how you look at the library. So this is your compound. This is the compound which has been given by the library. And when you look at the spectra, they are quite identical. And it gives you some information. It gives you similarity index. So it will tell you that the similarity index has to be there somewhere in this index. SI 97, similarity index is 97. So this peak is matching with this peak. So this is your compound. This is the spectra from the library, and both have 97% match as far as the spectra is concerned. So it is most likely to be your compound because the similarity index, which is given here as 97, is quite good. So this index tells us how close is this your compound with the spectra in library. And if that has got a good match, it will give you very high points here. So 90% is a good point. So we can consider it is matching. So this is called as a relative abundance spectra. Now this is the spectra taken from, from the library. This is the spectra of your compound. Now how to make it relative? Whatever information you get, you have to find out which is the base peak. Now this is the base peak, which is always considered to be 100. And with respect to this base peak, all other intensities are calculated and you get a mass spectra. Here also, this is the mass spectra taken from the library under the same condition. You are considered a base peak, whatever may be its concentration, this is considered as 100. And with this 100, all other intensities are calculated. So the relative abundance is always calculated on the basis of base peak, considering it as 100, all other intensities are calculated, and you get a spectra which is called as relative abundance spectra. So whatever may be the concentration, relative abundance spectra would be every time same. It will not change. Okay. So that is why it can be used as a good qualitative analysis tool. So this is again another compound which is matching well. These are compounds which are matching well, and here also. But the structure of the compounds are slightly different. So you have to understand other parts also in this to decide which one is your actual compound. This is again a spectra of acetophenone I have taken just to highlight how advantageous it is to have a GCMS over a GC. Now suppose I have a compound like this along with another molecule which has the same molecular weight of 120. Let us take the compound is say propylbenzene. That is, instead of acetophenone on this side, there is a C3H7 group attached to this phenyl group. Mass is 1D. So both of them elute at the same time. Okay. Now I am not sure which is, both of them have same mass. And if I take the spectra, it will show me odd spectra because it will also show me something from acetophenone. It will also show me something from propylbenzene. Now that these are the possibilities that I have one compound which could be acetophenone. There could be another compound which could be propylbenzene. How can I make sure? So what I can do is I take 120, and if I take 120 from both, I will get both the peaks coming at the same time. But in one case, I'm getting 105 as the base, and propylbenzene 91 as the peak. And if I see those two peaks, what I do is on my Prometheus, I will do SIM analysis for some time for 91 and some time for 105. And I will see two peaks, one for 91 and another for 105. And they are both coming at the same time. And what I can then say that there are two compounds, one is propylbenzene, another is acetophenone. Okay, now this is MS versus MSMS. So if I have MS, I have inlet ionization, one mass analyzer followed by detector. If I have MSMS for GC, again ionization would be EI. I have one mass, then one more fragmentation system, one more mass analyzer, and then it goes to detector. Now, when I have this kind of a system, what is the advantage of MS? That is what we have to check. Why unnecessarily have this kind of a complicated system when we can get work done by a single system like this? Now, when we have MSMS, we get additional additional specificity. And in case of GCMS, if you are only interested in qualitative analysis, this is good enough. You are interested in quantitative analysis with the simple matrix, this is good enough. But when you have to analyze the matrix stuff, like you have to analyze the food matrix for pesticides, I have to analyze pesticides in meat or in a given matrix, I require this kind of specification. Select one, determine it in the second mass analysis. Very important. And here I cannot do that. I can select only one ion and goes to here. I can select only one ion and that goes to here. I can select one ion here, fragment it, and select one of the fragmented ions to go to the detector. So if there are two ions which have same mass, they will go to the detector together. Here is one mass which gives me different fragment, and if there is another mass which gives me different fragment, when I sit here with that particular mass, I will be only able to detect one out of those two, and this way I will get a better selectivity. And that is why in the food analysis, pesticide residue analysis, GCMS is preferred. Okay, so how we do it? We recruit dissociation cell, and that cell will take the ion from the first quadrupole. So on this side there is one quadrupole. This is called as a collision-induced dissociation cell. There is one more quadrupole here. So in this quadrupole, you use a SIM mode, select one ion which you want to fragment. So this ion comes here. You apply an energy to it, so it starts vibrating. RF field is applied, so it starts vibrating like this in this area. On one side, you put a leak of argon gas, and this argon gas will collide with this ion which has got higher energy, or which you are making vibrate in this field. Because of the collision, this ion will fragment, and those fragmented ions go to the next quadrupole which is on this side, which will separate, and the detector is beyond that. So the system looks like, what is this collision cell? It is called dissociation, a quasi-molecular ion by accelerating these ions into the cell and then applying the collision energy, kinetic energy, and colliding it with gas, nitrogen or argon present inside the cell, and then transmitting these fragments into the next quadrupole, Q3, from a high pressure zone to a low pressure zone, because quadrupole has a low pressure. You transfer them and then scan them and measure them. Okay, so that is how you can get this is important in quadrupole quantitative analysis, triple quadrupole quantitative analysis, which is called as MRM scan. In addition to that, there is a precursor ion scan, neutral loss scan, all these kind of events. I will deal with all of them in the next lecture, because where I will talk more about LCMS and all these scan events I will cover there. Here I do not want to cover that for the reason that I had to cover some aspects which are common there. That is why I covered detector here. I covered vacuum system here, because detectors and vacuum system is common here also as well as there also in LCMS system. So I spend more time on instrumentation here. The application side of GCMS and LCMS I will cover in the next lecture to some extent. So this is how this system look like. This is first, here is the ionization, this is the collision cell, this is the next quadrupole, and this is the detector. Okay? So this is how the triple system, or to which we call as GCMS systems, look like. These all things I will explain time, because if I start explaining all, so product ion spectra, and then SRM or MRM, and then there is something more. So I will just explain MRM here quickly. This will be again explained otherwise. What is done? out of many ions coming, I have selected one ion. It is taken, it is broken into pieces, fragmented. All the fragment ions go to next quadrupole. Here also I select one ion and allow it to go to the detector. Okay. So by this way, one ion is fragmented to give me another ion, and this is a very selected reaction or transition. The original ion giving me a ion which is called as a product ion, and I measure this transition in my mass analyzer, and this is very specific to one particular compound. So when I analyze this, I'm only analyzing that compound, I'm not analyzing anything else. So when I look at this transition, only this transition will be given by one particular molecule, and that is how I can have a better selectivity in measuring, and that is why it is called as selected reaction monitoring or multiple reaction monitoring. And difference between SIM and MRM I will talk next time again. Okay, so this is what happens if I have SIM, you get very high background, but when you have SRM or MRM, your background gets reduced. You just don't see your peaks here, and here you can see your peaks. Here the same thing, you are not able to see peaks here, here you can see them. So wherever we have done MRM, you can see 265 giving me 210. So when I'm doing this kind of a transition, which is one particular ion giving me a product ion, and when I'm monitoring that, I get a very good sensitivity with no noise or no background. Here there is a background, here there is a huge background, here there is a huge background. Now because of MRM transition, all this background goes, and that is what the juggler has done. He has suppressed the background by MRM, and he gets very nice peaks here. Okay, so this is how the background can be suppressed by using MRM transition. Okay, so this is again all the scan events. As I said, I will take it tomorrow, and there are few advantages of that also I will consider tomorrow. Scanning speed and other parts I will consider tomorrow, because I think the time is coming closer to end. I have to answer some of the questions. One example of the MRM transitions, you can see 379 pesticides are analyzed in 25 minutes in one single run by using the GCMS method. Now you cannot think of a GC which can analyze 379 pesticides in one run in 22.5 minutes. But just because of MRM transitions, we can do that because we are not worried about the good separation in GC. Our GC gives a poor separation, but the separation is carried out in a mass analyzer, which does a beautiful separation of all those pesticides one by one, and you can quantitate these pesticides at picogram level by using a MRM transition. So in food matrix, when I want to measure so many pesticides, I can apply the method using GCMS or sometimes. So we come to a last slide, the limitations of GCMS. One advantage of a GC is that we have a capillary column, and capillary GC is used with MS, and capillary GC is the best method for separation. LC doesn't give you that kind of a separation which GC can give. Any column in GC will not be able to give of hundreds of columns. Capillary GC has that advantage. It has much better separation efficiency. So GCMS, when it is used along with capillary column, it definitely gives you advantage. The peaks in capillary GC are always sharp, and when the peaks are sharp with high intensity, the signal to noise ratio will be higher, so it gives you better sensitivity and better selectivity. Much better separation, that means you are doing much better selectivity in the separation in the GC itself. Another advantage is that it gives you library touchable spectra. LCMS has no library, will be able to guide you to the compound which is that is my idea. And then when you have GCMS, you have less interferences, especially when you want to analyze biological matrix by using the GCMS. complication because biological matrix will not interfere. Biological matrix will interfere more in case of LCMS because those matrix molecules, they will be soluble in mobile phase. Here, when you use a GC which has got a carrier gas, which will not have any solubility for those molecules, you hit them in the injection port, vaporize them, and then take on the column. You are not trying to do that with biological molecules. So you get less interferences because of GCMS. What are the limitations? It is only used for volatiles. Non-volatiles require derivatization for converting into volatile compounds. Only you can analyze by GC. So there is some possibility of some non-volatiles can be converted into volatiles and they can be analyzed. Molecular weight up to maximum 1000 Daltons, or some instrument 150 or as a sales gimmick, but then the maximum molecular weight which can be analyzed by GC or GCMS is only 1000 Daltons. So that's the limitation. There are many molecules much above when we try to analyze them by LC. There are a lot of all those compounds cannot be GC. There are only 10% which can be analyzed by GC. That is what I said. 90% of the organic and biological samples are non-volatile and thermally labile. They cannot be analyzed by GC. Okay, so that's one limitation. And another limitation you can consider: no detectors in series. Most of the detectors in GC are destructive detectors. They have flame. So you cannot connect FID to MS. But in case of LC, most of the detectors are non-destructive detectors. So you can consider UV visible detector, you can consider refractive index detector, you can consider fluorescence detector. All of them are non-destructive detectors. So you can connect UV to mass spectrometer, you can connect fluorescence to mass spectrometer. So that kind of advantage you get. So you can use two detectors and you can get some information on visible and then you get additional information by MS. So this kind of combinations of using detectors in series is possible in case of LCMS, which is not possible in case of GCMS. So because of these limitations, we require LCMS, and more about LCMS we will try to learn them on the lecture or in the lecture which is going to be on the 30th. And whatever I did not cover today, because especially MSMS part, and I know if I would have covered it at this stage, this MSMS part, it would have taken you probably more time to understand, because it has almost already last 2 hours you have been listening to me continuously and come to some kind of a saturation. And I feel I should explain you, because in case of LCMS, we are going to talk about LCMS right in the beginning itself, because after ionization, I'll go to mass analyzer, I will talk about this concept of MSMS, and I'm not going to talk about detectors and vacuum systems, etc. So I got a lot of time there to talk about MSMS, and we will definitely try to cover MSMS part, because what is required in the industry is LC-MSMS. Nobody uses LC-MS alone. So LC-MSMS is the technique which is used in industry maximum, and that is why I decided to cover MSMS part there, not to that extent as far as GCMS is concerned. Okay, so I think that's the end of my presentation. Thank you. I think because of that, I could cover it in time. So I said 2 to 4, and I tried to manage that. Thank you very much for your attention. I would like to, let me complete. I would like to thank all of you who have attended my lecture throughout without breaking any time. Probably you could have had your tea while there and listening to my presentation, which I could not do, and I could not sleep. But then to manage to talk continuously for 2 hours and give you some information about GCMS maximum. I hope you like the topic, and if you have any questions, I'm open to take all the questions.
Yes, sir. Thank you so very much, sir. It was indeed an exhilarating experience listening to the entire instrumentation, functioning, and applications. So I'm sure the participants have gained a lot, because I can see a lot of questions that have come up.
Oh my goodness.
I'll
Okay, good.
start with, yes, sir. So I'll start
Yeah,
with
please go
one
ahead.
of the questions says, Mr. Syed says, which instruments are required for GCMS sample preparation? If you could highlight on that.
Yeah, normal instruments which are required for sample preparation for any of these techniques will be simple liquid-liquid extraction, starts with that. If it is biological matrix, you can also use instruments like initially protein precipitation. If proteins are there, then use liquid-liquid extraction. You can use solid phase extraction. You can use solid phase micro extraction. And there is one more method, especially for etc. analysis. There is some method which is Quitcher's method. Okay, so that method Quitcher's method. Okay, so this is the quick
Sorry to
stands for
interrupt,
quick,
sir. There is,
easy.
yeah.
Yeah,
Hmm.
it is called
Your
as.
voice was breaking, sir. Yeah.
Oh, is it? Are you getting it now?
Yes, sir. Yes, sir. It's clear now. Yeah.
No, it is called Quitcher method. So Quitcher's method is a good method for GC sample preparation, especially for analysis in complex matrix. And it is Quitcher stands for quick, easy, cheap, efficient.
Okay.
And it is and is a form of term UH, something like that.
Okay.
Quitcher is one of the
Okay. Yes, sir. Sir, again, your voice is cracking. I mean,
is it
slight in
so?
internet, yeah. I can hear some part of it, and then suddenly there's a
Suddenly, okay, I don't know if some
yeah. Now I can,
disturbance. Now
yeah.
it is
So now
okay?
I can hear you. Yes, sir. Yes, sir. Absolutely.
Yeah, okay, fine,
Sir,
fine.
moving on to the next question, sir. There's also a question asking about what is the detection limit of GCMS.
Okay. Now, GCMS generally can go down to PPB level very easily. And with MSMS, you can even go down than that. Okay. So, generally, we talk in terms of nanogram
Okay.
to picogram. Okay. GCMS and MSMS can. Okay. So,
Okay.
GCA can go up to certain level, nanogram level. MS can go up to picogram
Hmm.
level or even below. Okay. 1 minute. I will just give me 1 minute.
Yes, sir. Meanwhile, all the participants can make a note that all of you will get a link for the feedback form. There are some people who have missed out who did not get the link. We will ensure that we will send you the mail again with the YouTube link where you can listen to the entire
Very, very
recorded
sorry.
video, and
Yeah.
maybe then provide you the, once you provide the feedback, you get the certificate. Yes, we can come back to the question answer round, sir. Yes, sir.
Yeah. Second question. Yeah.
Moving on to the next question. Actually, yes, couple of them have asked the same question. Which type of software is apt for GCMS?
Every manufacturer has its own software. Okay. But if you're talking about library software, then there are two main libraries, NIST and Willy. So either one is good. Okay. Some people will prefer NIST, some people will prefer Willy. Willy has more number of spectras and they have little better classification. So there are a lot of repeats because of that, because some compounds can get into one area as well as in another area. Okay, so compound could be solvent as well as it could be toxic. So it can come in two different areas. So sometimes Willy gives you more number of spectras, but repeat spectras. NIST is also good. So you can use one of these two libraries. Otherwise, the software for each instrument is made by the own manufacturer, and each one has separate kind of a software, so which they use.
Right, sir.
Yeah.
Yes. So a lot of them have asked about result interpretation.
What is it?
A lot of them have asked about result interpretation. GCMS result interpretation.
Yeah, okay. No, that only comes because of the experience. Okay. And there are a lot of books on structural elucidation or fragmentation rules. If you have those books with you, you read them and try to look at the spectras and try to analyze the spectra, understanding those rules. And probably with practice, you will be able to do that much better. There is always two things required. One thing is a good knowledge of organic chemistry.
Hmm. Hmm.
Okay, and then good knowledge of mass spectrometry and good. So it is not just logic. It has to be a scientific logic. Okay, so if you have that logic, analytical logic. So I probably there could be a new term, analogic.
Hmm.
If you are analogic, you will be able to analyze the spectra much better.
Okay.
Yeah.
Okay. Yes, sir. Yes, sir. Then another question Mr. Vikas asks is, while performing GCMS characterization of bioactive compounds, what is the effectiveness of using GCMS for the sample analysis, for the characterization of these bioactive compounds?
Now, if the bioactive compound is volatile, you can definitely go for GCMS. Many a times, bioactive compounds are non-volatiles. Hello, are you getting me? Hello? Hello, Kavita? Hello? Is there any disturbance there? Yeah, but I'm not. Are you able to get me? What is? Are you able to listen me? Is it clear? No? By chance, if I have done something here? No, my thing is on.
Ma'am, unmute. Ma'am, unmute yourself. Ma'am is mute.
Okay, yes. I can hear you now, sir. Yes, sir.
Yeah, now you can hear me?
Sorry for
Okay.
that.
Yeah, sorry.
Yes,
Okay.
yes,
Yeah,
yes, sir.
I was talking about the active compound. Okay, so if the compound is volatile, you can definitely use GCMS for that. But many a times the compounds which are analyzed, which are plant-based compounds, they are non-volatile. So you have to go for LCMS. And if you go for LCMS, there is no library. Okay, so you have to rely on your background. Okay, and when you have to have LCMS there, because with LCMS you will not get fragmentation. So you will require to have LCMS. So some of the flavonoids people have done by GCMS, even those flavonoids were not volatile. What they did, they derivatized those compounds
Okay.
and made them volatile.
Hmm.
So that way you can then use it, and then structural elucidation is possible because there is a library, and library can give you some information about that. Okay, there are two ways. You run it on LCMS and analyze it by yourself, because there is no help from the library. Okay, while GCMS there will be help from the library if you derivatize them and analyze them. Okay, and it is always good to have good information, because some of my students who have worked on that, how we proceeded, that knowing the plant, we did a lot of literature survey. We found out what are the compounds which are already been there, and they have been already identified. And
Present.
that there are, for example, if there are saponins in one compound. Okay, so this plant has saponins. Now, out of any saponins, which is the saponin? Now, when we get this LCMS and we get a molecule given compound, then we look at if it is saponin, whatever saponin information we have, we collect all these saponin mass spectra from different literature. Then look at the molecular weight of saponin which we got. Try to find out if this molecular weight is been given anywhere else, any of the saponins. And if that is given, then we say probably this would be saponin. Then we see if MSMS spectra is done on that saponin. Then we do MSMS on our saponin. And if this match, then we
And
can
try
say
to
this.
correlate.
So that is how we do the job mostly. Because otherwise it is very difficult to find out the structure of a compound. Okay, so
Mm.
yeah.
Yes, sir. Sir, so as you rightly said, like one of the limitations of GC is that most of the biological samples which are non-volatile or which are thermolabile, they
Yeah.
cannot be directly analyzed using GC. They
Right.
need derivatization. So in
Correct.
that context, like I am from biology. So I remember when I had to do the FAMES analysis, fatty acid methyl esters from bacterial cells, I had
Yeah.
to derivatize and then I could do GC.
Correct.
So in
Exactly.
context to that, sir, what is the status of what is the ease of derivatization procedures availability for biological samples? Like, is
Yeah.
it easily available for most of samples, or very limited samples can be derivatized?
Yeah, because there are lots of different derivatizing agents. Those can be used. Okay. So depending upon which group you are derivatizing, because what you are doing, you are aiming or you are looking at one of the groups on your compound, which you are trying to attach this derivatizing agent, so that that becomes a non-polar, because of its polarity, it is not able to get volatilized. It breaks. Okay, but when you bind something to that group, it becomes inert, and then it becomes possible to evaluate, and you can volatilize it and analyze it. Okay, so you should be able to find out that group which can bind to your compound and able to derivatize it. And then the thing is, derivatization should be complete. Okay, and it should be fast reaction. It should not be
Okay.
reversible.
Okay, sir.
Okay, and then there should not be some other byproducts which get formed, which will interfere with your analysis. So there are lots of problems when you try to work with derivatization, and especially if it is a complex mixture, you are not sure whether this particular agent will bound to your compound or it can bound to some other interfering compounds also.
Others.
Yeah. Yeah.
Right, right. Okay, sir. Then Mr. Rishiraj asks that what is the best condition for analysis of methanol and formaldehyde using GCMS?
Again, there is some
Methanol
disturbance.
and
Yeah, what is
formaldehyde.
it? Mm-hmm. Yeah. No,
Yeah.
I did not.
So the question is, what is the best condition for analysis of methanol and formaldehyde using GCMS?
Yeah, I would prefer them to be analyzed by headspace rather than directly putting them.
Headspace,
Methanol,
okay.
yeah. But methanol can be directly analyzed if you have, or better way is to analyze it by using the headspace GC. Okay. I do not know what is the matrix, in what context
Okay.
to analyze it, because he's only talking about two compounds. In what? Whether it is in formulation, whether it
Yeah.
is in, yeah,
Right.
everything will depend on that. Okay. So it's not
Right.
perfect question. I mean, if he explains what compounds these are and in which
Yeah, it's
matrix.
vague. It's vague. He needs to be specific.
Yeah. Correct.
Okay. Right, sir.
Anything
Sir, one more question says that, yes, sir. In one of the studies, GCMS studies that were carried out, when the column was shifted from C9 to C12, the tailing increased. And when the peak height reduced between the same C9 to C12. So the person is asking what could be the possible issues, or how to go about getting, proper resolved peak,
that
so
means
that the tailing can be prevented.
column is shifted from one unit to other unit. That is what he's saying. And then C9, C12
Yes,
hydrocarbon, they showed a different
yes.
intensity reduced or something like that. Is it?
The tailing increased. Right, right. The peak height reduced, but the tailing increased.
And the column was shifted from one unit to other unit. Shifted means what? It was
C9 to C12.
other GC. Is it
As
that?
in the analysis.
No, during analysis, how what?
It's not specified correctly, but
What he says, what is that
no,
first
one
type?
analysis and second analysis. One analysis using, sir, it says that the first analysis was carried out in C9, the other was
C9.
carried out in C12, but they were looking for the best condition and best separation. Yes, sir. The tailing was going higher as we were going from C9 to C12. I think it's a part of standardization question.
No, what does it mean by first analysis were done on C9
Yes, sir.
and
Sir, I think the person is trying to say that they carried out maybe standardization experiments that they were carrying out at using different columns, and maybe as they increase the from hello, Ajit sir, can you hear me, sir? Datar sir? Datar sir, can you hear me? Sir, you have muted yourself and we can't see you.
well, what does it mean? What does it mean by
Uh,
C9 and C12?
yeah. Sir, is possibly, hello? I missed him. Okay. Okay, in that question, for that question, maybe I can get back to sir, and once he replies, I can give the answer to the person, the concerned person. So, yes, sir. Sir, should we take that last question, or maybe I'll mail you the question? Sir, we cannot hear you, sir. Unmute.
Yeah, okay. Yes, please go ahead.
Yes, sir.
Now it is clear?
Now I can hear you.
Yeah, okay.
Yes, sir.
Mm-hmm.
Sir, so, yes, sir.
Yeah.
Sir, so
Yeah.
should we
Tell me
take this
next.
question, or I'll mail you this question?
This question,
Sir,
whatever
with
just
that,
now you
most
asked.
of the questions are sorted. Okay, sir.
Yeah. Any question
I
is
will
there?
mail you, sir.
Yeah.
Nothing, sir. One simple question asked is, does it mean that scan mode refers to qualitative analysis and sim modes for the quantitative
Quantitative.
analysis?
Generally, these are thumb rules. These are thumb rules.
Right.
You use scan mode
Okay,
also,
done,
some
sir.
other analysis also. Or TIC also can be used for quantitative analysis.
Okay.
Okay.
Okay, sir.
Yeah.
And sir, maybe one last question that we can take before closing.
Yeah.
Analysis sensitivity has decreased. What could be the possible causes for it?
There are number of causes
The
for a drop.
sensitivity of analysis has reduced.
Yeah, there could be a number of causes for that.
Okay.
Not only. Okay, so unless
Right.
we know the other conditions of analysis, it is very difficult to say what could be the condition because of which the sensitivity has dropped. Okay, so sensitivity can drop because of many reasons. If we are using GCMS, there could be many reasons because of which sensitivity can drop. Okay, one thing is, again, if is some information is coming, there is right from your column or right from your injection port to the detector, there are many places where the background can come, and if background increases, it will drop. Okay, so the background can be one of the cause for drop in sensitivity. And in such a case, what is to be done is you run your standard OQ. Okay, run your OQ standard, check what sensitivity you are getting. That will confirm that there is nothing wrong with the instrument, and there could be something wrong with your sample itself, sample preparation itself, which has made it drop in sensitivity. Okay, and then look at do also call as tuning of the instrument, see whether it improves further, because when you do tuning instrument, the parameters which were responsible for dropping signal will come back to its original and probably will regain your sensitivity. Yeah.
Done, sir. I think yes.
Finally, how many there?
I think that's all, sir. We'll stop. That one specification. Sir, we have around 450, sir.
Oh, good.
On YouTube.
Yeah, that's good.
Yes, sir.
Okay. See you then.
Yes, sir.
On
sir, with that, yes, sir.
Yeah.
On the 28th. Yes, sir.
Day after tomorrow.
Done, sir.
At the same time. Okay?
Yes, sir.
Thank you. Thank you all. Thanks to
yes, sir.
all your colleagues who have done.
Thank you very much, sir. Datar, sir.
My pleasure always. Okay, bye-bye.
Yes, sir. Yes, sir. Thank you so much, sir. Yeah, bye, sir.
Pleasure. Yes, bye.
Thank
Yes, sir.
ma'am.
Okay, dear participants, yes,
No, ma'am. Continue, ma'am.
wait. Yeah. Dear participants, yes, some of more questions are there which will be mailed to Datar sir, and accordingly you will be replied back and the response will be given. Also, I would like to take the opportunity to thank all our people who are involved in this system. Sir had another appointment, so he had to leave. Well, I would like to thank Principal Sir, Dr. Kiran Mangaonkar sir, who has been always supporting and headstrong in encouraging us for such events. Later, I would like to thank my colleagues from FIC department for arranging everything, for planning and scheduling things. Other colleagues from the GNID department and Khalsa College. I profusely thank the IT support given by Mr. Aldrin, Mr. Ashish, Sham sir, and thanks to all the participants who have made it possible. I think, yes, there has been some error with the mailing list, because of which some of you have not received the email. We'll work on that. Irrespective of all the technical things that we face, we will provide you the proper YouTube link. You can go through the videos, the people who have missed, and once you share with us the feedback form, once you fill it, immediately you will be given your certificates of participation. Second point, again on the 28th of May, that is day after tomorrow, we will be meeting for the LCMS workshop with Datar sir, which will be a continuation of what we did today and forward. Again, it will be sharp at 2 p.m. In case anyone is having any kind of trouble, my number is given on the brochure. Kindly WhatsApp me your queries. Yes, with that, I think I can announce the formal closure of the event for today. Thanks to each one of you. Thank you. Have a nice evening.